Okay, I'm going to show you how to set up a table that can find Pearsons Correlation Coefficient. I'm assuming you've already looked at the videos for working out standard deviation. I'm also going to show you how to work them out a different way using Excel as well. Okay, so I've got the data. We've got two sets of bivariate data, the X variable, which is the explanatory variable, and the Y variable, which is the response variable. Okay, so firstly, I've set up this table. We need to find the sum of this times this. Okay, so the way we do that is for every x value, we need to find x minus x bar on standard deviation. And for every y value, we need to find that y minus y bar or mean on standard deviation for y. Then we need to multiply it. So we need to find it for each one, then we need to sum that up. That's what that means, okay? And then we need to multiply by 1 divided by the sample size minus 1. Okay, so let's get started. I'm going to first show you how else we can calculate means. Okay, so we can just go equals average of the x values and equals average of the y values. So we're just treating them the same as univariate data at this stage. Standard deviation. Now you can go up to formulas, function statistics, scroll all the way down to the S's. Now that's standard deviation when you're looking for population, but we're looking at sample, so we go for that one. So we want to select, we're looking at SX, so we select the X values, enter, and go OK. And same again, more function statistics, S. If you want to type in stdv, that's fine as well. Make sure it's .s. And say OK. So these are our standard deviations. Our sample size, we can just say equals count of either one of these, because they come in pairs, or we can just count them up ourselves. Alright, so in this column we want to say x minus x bar divided by sx. Okay, so equals this value minus x bar. We want that, let's start again. So equals x minus x bar, and let's put it in brackets, and divide by sx. Enter. Now, in order to be able to drag this down, because this is a fixed cell here, and we need that to be a fixed cell, we need to put dollar signs in so that we can simply drag and not have to retype it every time. Okay, now we can simply drag. Okay, we can now do the same for y. So this is y minus y bar, the mean. Let's put it in brackets and divide by sy this time. Again, we need to fix these cells. We need to fix the y bar cell, and we need to fix the sy cell using dollar signs. And then we can drag. Okay, so this is simply equal to this value times, what just happened, start again, equals this times this, enter. Okay, now because the next one is going to be that times that, there's no fixed cells, we can simply drag. So now we want to find the sum of all these values, which is this part of the Pearsons calculation. So that equals sum of those values. Now over here, next to R for Pearsons Correlation Coefficient, we want to type in this, finish off this formula. So it's 1 divided by, in brackets, n minus 1, close brackets, times, now because we've closed brackets, this times is in the numerator. So times this sum here, which is this here. Oops. Okay, I need to fix that. Let's start again. So equals 1 on n minus 1 in brackets times that. Okay, so we get a Pearsons correlation coefficient of 0.89, and then we can go over to this table here and look for it. It's a positive 0.89, so that comes in between 0.75 and 1, which means it's a strong positive linear association. Okay, and we can check this by graphing a scatter plot. So if we select that and we go insert scatter plot, now this is something you do first. So you do your scatter plot, decide on what you thought, whether it was a linear association or not, because the Pearsons correlation coefficient only works if you make the assumption that it is a linear association. So initially you should look at it and say, hey, yeah, that looks approximately linear. So I'm not going to worry about changing the titles, that's in another video, but that looks linear to me and it's reasonably strong. But this calculation says it does fit in the strong positive category and it is linear. Alright,